Hi friends, let's have some fun with embeddings today. We know computers can understand only binary numbers, zeros and ones. We use embeddings to convert text into numbers so that we can use computers to solve NLP and LLM use cases, right? So the embeddings, they have two aspects. One, they convert words into vectors of real numbers in a high dimensional space. Okay, for example, this is how it look like. We'll come to it in a second, but here we have a vector in a very high dimensional space and it has a size of 768. Okay, this is an example of an embedding. And the second aspect is the semantic relationship between words are captured by the relative distance and the direction. Okay. To illustrate this concept, the second one, we are often given examples like this, right? King minus man plus woman is equal to queen. Other example is Paris minus France plus Italy is equal to Rome. There are numerous examples like this. So today, let's check if it is indeed correct. Okay. So at a conceptual level, this is how it looks like. So here we have a two-dimensional space, but here we mention it's a high dimensional space, but this is only two-dimension, right? So this is for illustrative purpose only. The real embeddings, those are often hundreds to thousands of dimensions. Okay. So in this two-dimensional, very simplified space, we have the origin here. We have a vector for the four words. Okay. The king, queen, man, and woman. So what we are saying here is, so we subtract the vector man from king. Okay. So we are subtracting this vector from this vector. So we would end up with this line, right? Or the vector difference between these two. Now add this difference to the vector woman. Okay, so we are adding this difference to the vector woman and this will lead us to the vector queen. Okay, that is what this concept illustrates. Let's check if that is correct. Okay, so standard libraries. We are going to use two embedding models. There are hundreds of embedding models. We will use one commercial and one open source. So Olama framework so that we can access open source LLMs and embeddings. And then we also use the commercial OpenAI. Okay. So let's say we have some text. This can be anything. Let's say it is king. Now here we are using Olama and our embedding model is this nomic embed text. Now this is the most or the highest number of times downloaded embedding model from Olama. Okay. So we just call this function with the model name and text that will give us the embeddings. So this model embeddings are of size 768. Okay. So that is what we meant by high dimensional space. Okay. And this is how the vector looks like. Okay. All these real numbers with size 768. Now OpenAI. So here we defined OpenAI client. All right. For this, we need an API key, which I have already stored in my environmental variables. Okay. So this is the most frequently used or the best performing embedding model from OpenAI, text embedding ADA 002. And we simply provide the text. So we get the embeddings. So this time, this embedding dimension is 1536. It's almost double or nearly double the nomic embeddings. Okay. And again, it's a high dimensional space and the numbers or the vector elements look like this. All right. Now what we are going to do is we will take these two examples and we will find out the embeddings for all these 4 vectors, and then we will do the vector operations, the addition, subtractions, and verify if these relationships are indeed correct. Okay. All right. So let's write some convenient functions. So the first one is, let's call it this find analogy, which will take these 3 words, word 1, word 2, word 3. And we are going to write another function, which is this get embeddings in a second. But given 3 words, what it does is it create embeddings or the vectors for those 3 words. And then it does this vector operation. Okay. Vector 1 minus vector 2 plus vector 3. Okay. Which is what this operation is. Okay. So we are computing the left hand side here. All right. Okay. Return the resulting embedding. And then, so the way we are going to do is, so these are the 3 words, right? So king minus man plus woman. That's what we computed on the left hand side. Now on the right hand side, what we are going to do is, so here we have selected a bunch of words which are all have somewhat similar semantic meaning. And then we compute the embeddings for all these 4 words. And we will check which one of these 4 is closest to the left hand side where we perform this vector operation. Okay. So essentially what we are going to check is, hey, which one is more correct? King minus man plus woman, is it equal to queen, or is it equal to princess, or is it equal to the duchess or lady? Okay. All right. So here we are finding the closest word. So we take this resulting embedding as an input, and then the word list. Okay. The word list is this list. So we take that list, and then we go over the list one by one. For each word, we compute the embeddings, and then here we are computing the Euclidean distance. Okay. So this word embedding, this is for each of the words in this list, and this embedding is the result of this left-handed side of the equation. Okay. So we are computing the Euclidean distance between the left-hand side, which is fixed, to all of these 4 which are on the right-hand side. Okay. So we compute the distance, and then we check which one has the minimum distance. Okay. And we return the closest word, whichever has the minimum distance, and we also return the distances to all 4 words. Okay. And then here we have another function which compute the cosine similarity. Now, as we discussed here, the relative distance and direction, okay, both are important for the embeddings. So here we have computed the relative distance. Here we are going to compute the direction through this cosine similarity. So we would have these 2 vectors. Again, vector 1 is on the left hand side, vector 2 is on the right hand side. What we do is we simply compute the cosine similarity, which is v1 dot v2 divided with v1 norm v2 norm. So here we are computing the dot product between the 2 vectors, and we are normalizing the 2 vectors, and this will give us the cosine similarity or the cos theta. Okay. And another handy function, just compute the similarities, which is going to call this cosine function, which is very similar to this function, which takes our left hand side embedding and the word list, and each one of these words, it will compute the embeddings, and it will compute the cosine similarity. So it will call this cosine similarity function, so it can compute the directionality similarity. Okay. All right. So here is our input data, and yeah, as I mentioned, we saw it here how to call the OpenAI embeddings, right? So let's wrap this into a function so that we can call for these 3 words as well as for each word in the list, right? So here we have created a function called getEmbedding, which is simply calling this OpenAI function. All right. So first, we have these three words. So we are finding the analogy or finding the left hand side of the equation. Okay, so we find the vector for king, man and woman, and then we do the operation king minus man plus woman, which is the vector operation, and the resulting is another vector, which is the embedding. All right, and then we pass the resulting vector and the list of these words so that we can find out which one is closest, both in terms of the distance as well as the directionality. Okay, all right, so we get the result, and here we are printing the results, and similar to the closest distance, here we are computing the cosine similarity. All right, so it says the result of king minus man plus woman is equal to queen. Hey, which is great. And let's see among these four what happened here. So the distance to queen is 0.51. The distance to princess is 0.65. To duchess is 0.68 and lady 0.70. Okay, so among these four words, queen is the most closest to the vector operation king minus man plus woman. Okay, that looks nice. And then if you look at the cosine similarity, which measure this directionality, so this distance should be as small as possible, right? The cosine similarity should be as high as possible, and anyway this will always be between 0 to 1. Okay, 0 means those are completely orthogonal. 1 means those are perfectly aligned in the same direction. Okay, so 0.88, which is great. And for the remaining three words, they still align in the same direction of LHS, which makes sense because these four words, those are not too different from each other in terms of semantic city. Okay, that looks great. And we are doing exactly the same thing, but this time instead of calling the OpenAI, we are calling this nomic embedding text using the OLAMA framework. Now let's look at the result. Now this one is also saying the result is queen, which is great. And then if you look at the distances, so this is 25.16, 28, 27, 27. Now here these distances are below 1, whereas these distances are quite high. But what is important is the relative distances, not the absolute distances. I mean, it does not mean that the embeddings are in this vector space are far from each other. Okay, only the relative distance is important. For example, here, if you look at these numbers, so those are 0.2, 0.3, something like that. It has even like that, right? Whereas if you look at OpenAI embeddings, these are much smaller than zeros. Okay, so that's why the distances are quite small with OpenAI embeddings. All right, so this is great. Now let's run the second example. So let's comment this out. All right, so again, on the left hand side, we have Paris minus France plus Italy. So we know the capital of France is Paris. Here we have Italy. This means we should get the capital of Italy. The correct answer is Rome. And here we have three other capitals, Berlin, Canberra, and New Delhi. Let's see what happens. All right, that's done. Now let's compute with OpenAI and this one. All right, so with OpenAI, we should have got the result Rome, but we got Berlin, but that's okay. Let's see how much is the difference. So between Rome and Berlin, there is a tiny fraction, right? I mean, it's a 0.000. So up to 3 decimal places, 590. The distance is exactly the same. So only in the 4th decimal point, the Berlin is closer to the LHS compared to ROM. Okay, but this does not mean these embeddings are performing poor. This need not be taken very literally, as long as they capture the semantics in terms of both the distance and the directionality. The embeddings does a great job in applications like RAG. Okay, all right. Now, if you look at the cosine similarity, again, Rome and Berlin, though they have highest similarity. So 0.835 up to 3 decimal places, they are the same. Now, using nomic embeddings, okay, this does a great job. So it indeed is Rome, and the distance is significant. So this is 12.99, let's say 13, whereas to Berlin, this is 14.34. Okay, so yeah, so among Berlin, Canberra, and Delhi to the LHS, Rome is the closest, which is correct. And the similarity, this is 0.86. The other ones are around 0.84-ish. Okay. I hope that gives you a little bit of context of these vector operations and how embeddings capture these semantics. By the way, these embeddings, those are coming from a deep learning model to which we feed lots and lots of text. So the model, it understands which words are used in similar context, which words are often come closer to each other, etc. So that's how the deep learning model find the relationships and the semantics between these words, so that when it project the words into this higher dimensional space, it is able to capture these two ideas, the relative distance and directions between semantically similar words. Okay. I hope you like this video. Thank you very much.